Hello everyone, I am Hanan Bashir. Today I am going to discuss lecture 10 and lecture 11 of CH104 in organic chemistry. So let's begin. So this is a slide which represents four coordinate complexes where the coordination complexes have four ligands in there. So this is Br4, Cr4, Pyridium 4 and Cl4, and they will have these shapes like tetrahedron, and this is square planar. So we have to keep this in mind that nickel and palladiums will have the square planar when it is coordinated with Cn, and here it is Cl. Then mixed ligand square planar complexes where the square planar will mostly have D8 configuration and it is mostly greater splitting energy. Then cis and trans geometrical isomers are possible with complex with two different type of ligands. So one is synthesized this PTCl2 and SL2, which is the platinum. Cisplatin is also used for the treatment of tumors and other cancer, and it is noteworthy that cis isomer is active. Five coordinate complexes, this example FeCO5, which have triangle bipyramidal, where square pyramidal will have VOOH whole twice 4. Uh, then the example where the molecular structure and infrared spectrometer of FeCO5 show that it is consistent with triangle bipyramidal, but in many cases that it also shows that at different temperatures different structures are observed, because this triangle bipyramidal and what we say, one second, and square pyramid have similar energies, so they can convert between them each other. Then these are the orbitals. Crystal field theory, the relation between color and complex metal. So it gives the relation between color and the complex metal structure. So it gives that if the electrostatic interaction between lone pair result in coordination, the energetics, how do they compare that when they're free atoms, then they will have very high energy. When they bond together, the energy reduces, and after that ligand d electron repulsion will cause the energy to increase again, and then there is splitting of outer d orbitals in octahedral field. So this is the pattern which I just said. It is initially very high, then low, then again high, and then splitting. Then ligand field theory is one of the useful bonding theory to explain the electronic structure of complexes. It is originated from crystal field theory of ionic crystal to metal complex systems. Then let us consider ligand field generated by six ligand coordinating octahedral to a central atom. So we see that there is the ligand field, which is the electron pair of ligands. Then dx square minus y square and dz square are oriented along direction of axis, whereas the other x, y, y, z are along the different axes. Then we can see that this is the octahedral splitting and this is tetrahedral splitting, where there will be 3/5 above the zero line, and here in this case will be 2 by 5 above the zero line. So this will be delta O is the octahedral splitting energy, and this is the tetrahedral splitting energy. Then ligand metal interaction. So how do ligands and metals interact? So we see that they align along the octahedral axis, which will be affected more, and hence they will have more splitting, which will be x square minus y square and z square. So they will have higher energies, and this will spoil the degeneracy of all these five orbitals. Then magnitude of CF splitting, there will be more splitting if we have in these cases that large metal will have larger delta, higher oxidation state will have large delta. Similarly, this is the order of the ligands which are attached. So Cn minus will cause higher splitting, and so on it will decrease across this order. Then weak field ligand, that low electrostatic interaction, small CF splitting, and high field ligand will cause high electrostatic interaction. Electron configuration octahedral. So just we discuss these conditions will enable us to determine whether this pairing will occur in the bottom or not. Octahedral, tetrahedral, and square planar. So this was a splitting in octahedral, whereas in tetrahedral, x, y, y, z, and x, z will have more energy, and in square planar, x square minus y square will have the most, then x5, then z square, and then xz, yz. So how can we remember it? We'll know that this is xy plane and square plane lies in a single plane of xy. So xy will always have higher energies. So x square minus y square at top, then xy, and then similarly z square will come, and then xz and yz. So this is the way where you can classify different splittings. So you can just look through them. Then high spin versus low spin. So how do we know that if an atom has high spin or low spin? So we can see that in the D4 to D7 configuration, which is given by Mn2 plus, Fe3 plus, Fe2 plus, CO3 plus, and CO2 plus. These all will have double type of configuration of high spin as well as low spin. In low spin, there will be pairing, but in high spin, there will be unpaired electrons. This is the complete order of the ligands which will have the splitting energies. And this was the different splitting just we discussed before. And this is the CFT summary. So how does it summarize that the color and magnetism properties are defined by the splitting energies, and this orbital molecular orbital theory can be used to describe the bonding scheme in these complexes. So this is the delta O just we discussed. Similarly, you can find delta O by seeing the difference between Eg star and T2G. Here also same. And from that, we have entered our lecture 10. Now we will go to lecture 11. So lecture 11 is quite short. So here we are discussing that how does these electrons are shared. So here we see that there is a bonding between nickel and uh, carbon monoxide. So first we do the splittings, and then after we bond we get these structures, this table I mean. Then 18 electron rule. So this is the rule by which we can determine the tendency of transition metal to use all its valence shells. So consider CrCO6. So this is 6 for chromium's valence electron and 6 into 2 for the each ligand, so total 18. Similarly, we can do for this also, we get 18, and FeCO5 also 18. So if it is 18, then it is high tendency of formation. Uh, this is actually a subpart of effective atomic number, which was given by Sidgwick, and it tells that the configuration of a noble gas is preferred after applying the same formula, that double for each ligand, and then adding the total atomic number of the coordination molecule. So 24 plus 2 times 6 is 12, and add them, we get 36. So EAN is only that much. And nature of early transition elements such as group 5 will have strong electrophilic and oxophilic nature. We have discussed this before, that they do not obey the 18 electron rule and will be always less than 18 electron. Then electron count made simple. How do we count electrons? So there are two ways. One is ionic method and one is neutral method. One neutral is that where we give zero charge on our central atom. So cobalt will have 9, and this is the valence electrons which we count. Similarly, in cobalt plus 2 we'll get 7, and then we add the total ligands and double them. So we get 12, and then we get total electrons 19. So this is favorable, but not that much, because it's not coming out total to be 18. Here we are getting 16 and we are getting 12 in this case. So we are doing this everything same. So we get, this is 18, this is 17, this should be 17. There is a typo here. This is 7 into 2, and this should be 34 by 2 and gives 18. And this is CO8. Then we find that this helps us to determine number of bond between the repeating central atom. So 18, so 8, since there is 18 and we need 18 actually, so 18 minus 18 should be 0, so there will be no bond between. Similarly, subtract 18 with this to 17, so we get 1, so we get one bond here. Similarly, 18 minus, I said this was 17, so it should give out 1. And similarly, if this is 15, we subtract from 18, we get 3, so we get 3 bonds between the central metal ion. And the 18 electron rule can be used to determine the central atom as well. And this is the last example where we see that the 18 electron rule is followed explicitly by each bonding submolecule. So we see that there is 4 electron from OC, that means CO carbon monoxide, 9 from rhodium, and 4 from this benzene rings half part, which is eta 4, and 1 for this bond between, which comes out 18. Similarly, here 3 from eta 3, carbon monoxide will give out 6, 8 from iron, and then 1 will be this bonding. So this number should be always certified that their sum will be 18 or nearest to the noble gas configuration. So that was all for our CH104. I hope that I was able to cover almost all the part. So thank you for your attention. All the best for tomorrow's end sem. Peace.